So we're continuing on with the 3.1 notes, and we want to look at some different notations for the derivative of y equals f of x. And so remember, when we're talking about a derivative, we're going to be talking about the slope of the tangent line at some instant, at one point, not at 2 points. Well, there were really two main mathematicians who were crediting for developing calculus at a high level. They weren't alone. Calculus was around for a while in some very non-formalized methods. The Greeks, there were some mathematicians from India, but Sir Isaac Newton, a very famous mathematician and even a more famous physicist, you would know him from like laws of gravity and laws of motion. Sir Isaac Newton really was instrumental in developing a lot of the ideas with calculus. He had a notation that is not commonly used. It was really poorly developed and ended up not being very useful, but there's his notation. Now, at the same time that Newton was around, there was a German mathematician named Leibniz, who actually a little bit younger than Newton, and he and Newton would correspond. They were colleagues. They wrote letters back and forth. And Newton shared a lot of his ideas about calculus with Leibniz. And Leibniz, it sounds like, also shared some ideas with Newton. But Newton was very slow in publishing his work. Leibniz beat him to the punch and basically got all of the fame and credit for developing calculus. But they were both probably stealing ideas from each other. And Newton, I think, was actually developing calculus ahead of Leibniz. But they both made really good work. Leibniz had a notation that he developed that was much more useful than Newton's, and one that you'll see us use this year a lot, dy over dx. This is very related to slope. If we think about what slope is change in y over change in x. That's what Leibniz is talking about here with that d. If you have seen in a science class, maybe physics, that should be delta y over delta x. This is a way to describe slope. And d for delta. D for a difference, a change, a very small difference. You could use the word differential for that, which we're not going to really explore at this time. There was also another Italian mathematician who had a very useful form. His name was Lagrange. And those of you who decide to take BC calculus, you'll actually learn a little bit more about some of the ideas that he came up with. But he was Italian, and he used f prime of x, or y prime, if you will, depending on how the function is named, to talk about the derivative, or the slope of the tangent line. So you'll see primarily we will use Lagrange's notation and Leibniz's notation. We will not be using Newton's notation. It just isn't useful. So for a couple examples, we're actually going to start with example 2, and we'll come back to example 1. But we want to find the derivative of each function by using the limit definition. And we also want to find the specific slope of the tangent line at the requested value. Those directions will make a little bit more sense when we dive into a question. And we're going to start with number 2. The limit definition, that is the one that I think you're going to find the most useful, is the limit as h approaches 0 of f of x plus h, so we have an input of x plus h, minus f of x over h. This is the one we developed in the previous video. The h gets a little bit confusing in this particular problem because of the fact that our function is named h. H is just some constant. We could rename that to a different variable, and just so that you have a little bit of exposure to some other common ways for people to write this, I'll use delta x as a variable. Sometimes students get really uncomfortable with that variable, but it's just a variable like y or anything else. Okay? All right, so I'm going to now customize this limit for our function. So the limit as delta x approaches 0, and I want to start with this, f of x plus delta x, or f of x plus h if we were using a different symbol. Basically, what I want to do is I need to go to my function and I need to replace my input x with x plus delta x. And I need to do that everywhere that the input x was written in the original function. So I have my input squared plus 5 times the input. And then there's a minus in my limit. and I want to subtract off the original function f. Might be weird to call it f in this instance. Maybe I should call it h, because that's actually the name of the function this time. So now I want to actually subtract off the entire function h. Now it is very important here that I include parentheses, because I'm subtracting the entire function, not just the term x squared. And this is all over delta x. Now if you tried substitution at this point, you would end up with 0 over 0, which, remember, does not mean not possible. It means that this is an indeterminate form, and substitution is not helpful at this point for the problem. We're going to try to rewrite this. So I'm going to expand out and do some combining of like terms for this expression. And so on the numerator, x plus delta x, quantity squared. Keep in mind that when you're squaring a binomial, you're multiplying it by itself. You will need to expand that out or use FOIL. When you do that, you would end up with x squared plus 2x times delta x plus delta x squared. That whole quantity, that whole variable delta x is squared. If you want, you could put parentheses there to help you understand that. I'm also going to distribute the 5, so plus 5x plus 5 times delta x. And I'm going to distribute the negative for the last expression, so minus x squared and minus 5x. And this is all over delta x. This is kind of an ugly expression, but it gets a little nicer because we do have some terms that are going to cancel out, which is really nice. And so really all I have left on the numerator is 2x delta x squared, and 5 times delta x over delta x. If you tried to substitute, and again, you'd still get 0 over 0. So we are not yet in a place where we can substitute. However, you might notice that all of the terms have a delta x. So I'm going to continue with my limit notation until I've used substitution. And I'm going to take delta x and factor it out. And when I factor it out as a common factor on the numerator, I can then reduce it on the denominator, leaving me with just the expression 2x plus delta x plus 5. I'm going to try substitution again and see, do I get something different than 0 over 0? And I should, because I don't have a 0 in the denominator anymore. I'm no longer going to write the limit notation because I'm now going to use substitution. So this would be 2 times x, delta x is approaching 0, plus 5, or 2x plus 5. The derivative, h prime, would be equal to 2x plus 5. This is the slope of the tangent line at any different x value. You might think that looks like a really weird slope. You may have expected us to come up with a number here, but here's why we're not. Let me just draw a little sketch of this graph. If you factored this, you could find out the x-intercepts are at 0 and negative 5. The graph looks something like this. Well, if I draw a tangent line to different points on this curve, what I'm going to find is that I get a different slope depending on where I draw the tangent line. For example, if I drew the tangent line right here, I would get a horizontal line, which has a slope of 0, and the derivative right there would equal 0. If I drew a tangent line maybe over here, you can see this line has a very negative, a very large negative slope, or a very large number with a negative sign for its slope. Versus they want me to find the slope specifically at the 0.16, okay, wherever that is. Just not drawn to scale, sorry about that. So we're actually going to find the slope of the tangent line here. Well, at this point we have a different slope than we do at some of the other points that we've looked at. This one would have a positive slope. This is why when we're looking at the derivative, they're giving us an expression here. Because depending on what our input for x is, we're going to get a different output for the slope. H prime of x, my output is the slope. So I want to now take my slope formula and use the 0.16, and notice it says h prime of x. The input here is going to be a 1 because x is 1. And what I'll find out is that my slope specifically at 1 is 7. A very steep positive slope here. So if you have a nice expression, you could just plug in x plus delta x or x plus h and use your limit and do some simplifying. Now, this next one is super weird. because this, and I'm actually going to use a little line to help us with this one, or a graph. We're looking at a line. And so we are asking to find the tangent line of a line, which is kind of a weird thing to even be thinking about. So this is my x-axis, this is the y-axis, and this is the line y equals -2. And I want to, at the point 3, -2, find the slope of the tangent line. Seems like kind of a nonsensical problem. And so what we're going to say is that if your function is a line, if your function, whether it's y or f of x, however we name it, if the function is a line, we're specifically talking, by the way, about functions, so we are not going to be talking about vertical lines right in here at the moment. We'll talk more about them later. But if your function is a line, then the derivative, let's say the function's called y, then the derivative y prime will equal whatever the slope of the line is. Instead of thinking the slope of the tangent line, this is already a line. So we're going to just use the slope of the line itself. Well, in this instance, this is a horizontal line, and the slope of this line is equal to 0. And so what we're going to say is that the derivative here, y prime, is equal to 0 for this entire line because the slope is unchanging. And so rather than thinking of the slope of the tangent line, since this is already a line, we're just going to use the slope of the line. That only is going to work, however, for linear functions. Let's look at